Hello everyone, welcome to the OneClass channel. My name is Fejiro, and I'm an honors Bachelor of Science student currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college level. If you need some homework help or further tutoring, check out the links in the description below. So with that, hope you're having a wonderful night. Let's kick this off for today with this question. So our first question for tonight is, what is a hydroxyl group? Okay, so with that, let's see what we're dealing with here. So when we think of a hydroxyl group, right, we're thinking of things that simply put, here's our main R group, okay, and then hydroxyl is just attached to that R group as a oxygen and hydrogen, hence how it gets the name hydroxyl. So you'll see things common things like alcohols and carboxylic acids as well. For example, if we were to draw an alcohol, any alcohol, let's say we have propanol. In fact, let me just do this just to make sure that we're on the same page here. What is a hydroxyl group? Okay, so like I was saying, propanol is an example. So it has 3 carbons, so 1, 2, 3. And then one more, but it'll be OH right there. This right here, that OH at the end, that is your hydroxyl group. Without the hydroxyl group, we would really just have propane. This is without the hydroxyl group. Another example of a hydroxyl group, for example, would be, let's use actually the pro, like 3 carbons, propanoic acid. Okay, so same thing here, it'll have, and then the branch out to the OH, but the C here will have that. So this is still your hydroxyl group, and it's called an acid because it's reacting over here to form like a, what's it called, resonance structure there. So that would be your, I guess, example, propanoic acid. Take out the the hydroxyl group from propanoic acid, and you end up with an aldehyde. I am blanking out on what the name is, but it'll kind of look like that. So actually, if we write it better like this, okay, and my naming for aldehydes is a little bit rusty, so I'm not going to try to name that. But the point being is that the common thing here is that we're trying to discuss hydroxyl groups. It simply can be just said that it's your OH attached to your R, which is your main chain. So it can happen one molecule can have several hydroxyl groups. So for example, if I had something like this, okay, I can have multiple hydroxyl groups. I can have an OH here, an OH here, and like an OH here. Each of these OHs are hydroxyl groups. So hopefully we've hit that nail on the head several times of what a hydroxyl group looks like. And with that, let's see what they said here. So a hydroxyl group is a functional group that contains an oxygen and a hydrogen, so that OH. Alright, and it's cool because hydroxyl sounds a lot like hydroxide, which is just OH minus. Sorry. So if you're having a hard time remembering, this is a hydroxide ion, so OH minus. And I hope I'm saying that right. Hydronium is H3O, and hydroxide, yep, OH minus, that's a hydroxide. So they're very similar in name, So that may help you remember that. Okay. And it can be found in the functional groups of alcohol, as we showed here with propanol, and carboxylic acids, which will be shown with propanoic acid. So yeah, and exactly, they do mention that it is a hydrogen bond, because exactly anything O, when O is attached to an H, this in itself is a hydrogen bond. So it increases the energy required to break that bond, meaning that exactly like you notice with alcohols and acids, they have quite high boiling points relative to like just like propanol will have a much higher boiling point than propane, for example. But yeah. So this is correct. Now let's move on to question 2. So with that, how do you get the degree of unsaturation formula? So I don't want, I can only cover my hand over my screen, but obviously you can see what it says there. But in a sense, we first explore, so first we'll write it down. How do you get degree of unsaturation formula? So first we need to talk about what does being unsaturated means, and we'll find that out by explaining what being saturated means. So a saturated carbohydrate, okay, looks, or hydrocarbon, that would actually, yeah, carbohydrate works too. Either way, saturated versions, think of it as a long chain of carbon and hydrogens. Sorry, we can draw that better. Yeah, we can definitely draw that better. Okay, this is saturated. Why is this saturated? Because it has the max amount of hydrogens per carbon. For example, what does that mean? Each point here is a carbon, okay? Right? And each carbon has a maximum amount of hydrogens it can attach to it. Just like that. Okay? And remember, when we're trying to figure out our formula for carbons, in saturated hydrocarbons, right? It's CnH2n plus 2. That is a formula for it. So you notice if we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, it'll be C10H22. That is 10 decane. That should be what it's called. But the point being here is that this is a completely saturated hydrocarbon. So now, with that being said, what does it mean to be unsaturated? So with that, let's actually draw it out. Okay, we're actually going to use the same 10. 4, 5, 6, 7, 8, 9. Okay, we're going to use the same 10 here, but the difference here is that there are double bonds present. It doesn't matter how many, as long as one, as soon as one shows up, it's no longer saturated. Okay? And there's actually a way to calculate the degree of unsaturation, aka how many what's it called? How many the number of double bonds, pretty much. Okay? And here actually does a great job of breaking it down. But the point being, right, is that if we were to now label the carbons like we did before, okay, 4, 5, 6, 7, 8, 9, 10, right? But now for the hydrogens, right, you have 1, 2, 3, 4, 5. Because it's a double bond here, it's only one each. And then there's a double bond here, only one. And then this one has 2 again, only one, 3. So you see here, if we actually did the formula, it would be C10 H 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. H 16, because there was 3 double bonds, which exactly accounts for 6 of them being lost. So yeah, sorry for all the notifications. So with that being said, let me just double check here. Sorry about this. Okay, so with that being said, exactly that's what it means to be unsaturated. Now what they've done actually is they've given us a very nice formula to be able to find out the degree of unsaturation. So now I was able to work on this off screen, and I do know this is correct. So to find the degree of unsaturation, aka how many bonds or rings you should be looking out for, you use this formula here. So what it's saying is that you want, for every carbon you have, you multiply it by 2. Okay, alright, plus 2 plus n minus x minus h. So what this means is that pretty much any nitrogen there you also add, but any halogen or any hydrogen you subtract, and you divide everything by 2. And in fact, we're going to use this formula to work on the 2 examples up here, okay? Because I predict that this saturated one will give us an answer of 0, and this unsaturated one will give us an answer of, I believe it will be 3. Okay, so now let's find out. 2C, right? So that's 10 times 2, that's 20, plus 2 plus 0, because there's no nitrogen, minus 0, there are no halogens, and then minus 22. Wow, and that equals 0, because these will cancel out with a 22. Now the C10H16, same thing here. We have 20 plus 2 plus 0 minus 0 minus 16 over 2. So 22 minus 16, we have 6 over 2. And yep, it is indeed 3. Now you're probably wondering exactly how did I get 3? And as you notice, we have only 3 double bonds. So whether, this is the tricky part here, right? When it's double or triple, think of it as, in a sense, adding a level of unsaturation. Okay, so in fact, we'll actually look at this table here. When there's only 1 degree of unsaturation, that's a very rare case where it has, actually this is an interesting thing, because 1 degree of unsaturation could also mean that it has 1 double bond. So with that being said, I think this is just including rings as well. So rings is the first priority, because for example, if we had only 1 double bond, you'll notice that the hydrogens instead of 16 will be 20, and then 22 minus 20 is 2 over 2. So exactly, so I would say if we were able to copy this table down, it would be either 1 ring, which is correct, okay, 1 double bond, and 0 triple bonds. Okay, that's how I would break that one down. Now, as it goes down in terms of degrees of saturation, exactly, like if you had now 2 degrees of unsaturation, which is now 4 hydrogens missing, quote unquote, in a typical sense like this one, or 2 double bonds, exactly, that's a possibility as well. 2 double bonds. Okay, I see how I wrote it. So it should have been like this, or 0 1 0, because it can definitely have a double bond without a, yeah. So with that being said, that is what we have here for sorry about that. That is what we have here for the degree of unsaturation. Is that definitely memorize this formula here as it is written. It's quite important, because then you can tell yourself what's the degree of unsaturation. And this table here, it helps you break down what you should be expecting. An example that I can think off the top of my head is benzene. Okay, this would be the last example, but pretty much this is C6H6. Using this formula, we have 14, okay, minus 6 over 2. All right, because we have 6 carbons, okay, multiply that by 2 plus 2. Okay, and 14 minus 6 is 8. Divided by 4, okay. Whoops, I don't know why I put 4. 8 divided by 2, 4, okay. Why? Because this is the degrees of unsaturation. Benzene, if I drew it out with the actual, I drew a ring, because that's like how it likes resonance, the resonance structure. But really, benzene is like this, with 3 double bonds and a ring. So being in the ring itself counts as a level of unsaturation because the ends aren't free; they have to connect with each other, which is that 1. And then the second one is going to be, well, the rest of them, the 3 left, is how you add up to 4 in regards to the degrees of unsaturation. So that is actually one of the best examples we have here. Because exactly, if the table went far enough to show 4, it would show that that was a possible combination. So for example, if we had a 3 degree of unsaturation, and I'm looking at this example here, so if I can highlight it, okay, this is what it could possibly look like. It's no longer benzene, okay, it's a ring, but with only 2 bonds. So it has 2 bonds, 1 ring, and exactly, that's how you still get a 3rd degree of unsaturation. But yeah, oh, they do talk about benzene. Yep, and it is 4 indeed. And they do mention that just because you know the degree of unsaturation and the type of molecule doesn't mean all of a sudden that you know what type of structure it is, because they show there's a bunch of isomers here that still have C6H6, but it's not benzene. These are all isomers of it because they have the same formula. As you can see here in this 3rd example, it has 2 double bonds and 1 triple bond, and triple bonds count as 2 degrees of unsaturation, so you can still get there that 4 degrees of unsaturation. So exactly, all of these are just different examples of a 4 degree saturation of a molecule, or a hydrocarbon in this case. So this is correct. So with that, let's move on to question 3. Hopefully something that's gives a little bit of a breather here. Oh, convenience. So this question is asking how many quarts in a gallon. Okay, so let's actually refer not to just the answer shown there, but to our handy conversion sheet here. And what does this say? So it says 1 gallon is equal to 4 quarts, okay? But we want to know the quarts in the gallon. Now, we can just straight up guess, right? But for this, I want to actually use this time to practice, keeping with your digits and your conversion factor. So if we said X gallons is what we have, right? We want to make sure we transfer it over to quarts, because although we know it's a 4-to-1 ratio, we want to make sure that we're applying the 4-to-1 ratio in the correct fashion. Okay, so to get rid of gallons in the numerator, you need gallons in the denominator. Okay, and it says here there's 4 quarts, so that would be what goes up here. Okay, and just like that, these two cancel out, and there you have it, X times 4, so it'll be 4X quarts. For any X that you get for gallons, it'd be 4 times the amount. If I had 2.5 gallons, that would be 10 quarts. So things like that, although it's relatively simple in face value, the important thing to take away here is that when you start getting into more and more complicated unit conversions, make sure you keep track of which units are actually being canceled and which are being added. But yeah, that's all I really have for this question. Let's see what it says here. Oh. Yes, okay, exactly. Oh, there's 2 different types of quarts. I did not know that there were different types of quarts and gallons. Good to know. Hopefully They're not going to ask you how many US quarts are in a Canadian gallon or a UK gallon, for example. That would be a headache of a question. But yeah. So now let's move on to question 4. Oops, sorry. Alright. So we have, what is a molar mass of sodium hydroxide? So, molar mass of sodium hydroxide. Now, the reason why I actually picked this question is for us to get familiar with the nomenclature, actually. Because the molar mass part is relatively straightforward in terms of finding it out, but it becomes increasingly difficult when you don't know what that name means in regards to molecular structure. So let's break it down. Okay, I like to draw a line right there. Okay, just because it usually separates and distinguishes what type of molecule you have. So we have a sodium and a hydroxide. Okay, so hydroxide, that's the one you kind of have to memorize, and we did briefly discuss it actually. So it is hydroxide, that's good. But if you remember, hydroxyl groups are just the OH. That's also what hydroxide is. It's just an OH minus, as we discussed earlier actually, right? And if you see the constituents of OH minus, that's just 2 nonmetals paired together, okay? And the reason why I mentioned that there are 2 nonmetals paired together is because remember the rules of ionic compound. So we know right now hydroxide is not ionic, it's just a molecular compound. But sodium is just Na, okay? Now, with that, it is a metal, okay? And now we want to make sure that we actually have the right amounts of electrons it likes to give away. So with this, you can either find it through its electron configuration to really understand it, or you can just use a periodic table and see that it's in the first column. Okay, elements in the first column like to typically just give away 1 electron. Okay, so it'd be Na plus. If you wanted to use the method of blank on the electron configuration, you just start with neon, and you'd notice that right away all the sodium has will be 3s1, and that 1 there tells that that's the only valence electron it can give away. And the reason why it gives it away is because to get 7 more electrons to fill its shell would be so much effort, it'd rather just give away 1 to become an octet. So with that being said, there's 1 positive sodium and 1 negative hydroxide. So to balance it out, all you need really is to just go 1-to-1 ratio. So this will just be NaOH. That is sodium hydroxide. So once again, this is an ionic compound because that's a metal and a non-metal. So metal and non-metal, okay? And now that we know what sodium hydroxide is, let's find the molar mass. So that one, as I said, is relatively straightforward. You just have to count your constituents. So 1 Na, 1 O, 1 H. Okay? And then sodium is 22.9. Okay? Oxygen is 15.999. And hydrogen is 1.008. Okay? And because it's just multiplied by 1, I just like to rewrite it on the side to keep things consistent. 999 1.008 8 plus 15.999 plus 22.90. You have in total 39.907. So yes, the molar mass of sodium hydroxide is 907 grams per mole. Just gotta draw that better. That right there should be the answer. So let's see here. Yep, they rounded a little bit different than I did, based on, I guess, the periodic table as well. Oh, did I really put? I missed a 990. That does change the answer just a slight bit. Let me see here what I get when I include the extra 0.9. Oh, okay, so I can see how they got 40. It's quite close to 40. Yeah, very close to 40. But yeah, so that's how you solve that question here. The trickiest part is knowing what sodium hydroxide is. Now, that was just a pretty much extra step, because sometimes they do just give you that information saying, hey, this is sodium hydroxide. Solve, go ahead and solve it. But sometimes when you're just given the name of the compound, it's important to just recognize how to separate and break it down to be able to get, the actual molecule. So with that, let's move on to question 5. Okay. How do you calculate the atomic mass of carbon given the atomic mass of its stable isotopes? So how to calculate so AMU of carbon given the atomic mass of stable isotopes. So that's honestly a great question, but this is actually what's even done in real life. So the thing is that finding carbon that's 12.011 or whatever it is, let's see here, yep, 12.011 grams in nature, that's almost that doesn't really exist like that. The reason why I say that is because each based on how they calculated the moles and everything else, you would typically have it to where for every, I guess if this makes sense, for every mole of a proton, it's around 1 gram. Okay, and the reason why I say every mole of proton is because think of hydrogen is actually a perfect example. Most of the times it's running around with just H plus, and you notice that its preferred state is just like 1 gram almost, like you see 1.008. That's around the mole of a proton, and neutrons equal around there too. A mole of a neutron will be around 1 gram in terms of that'd be the molar mass, gram per mole of neutron and proton. Now knowing this though is because when you have like carbon and stuff, right, they don't have a half amount of proton or half amount of neutrons and stuff like that. They have full-on neutrons, full-on protons. So you find that in nature, right, you'll see things like this where it's like carbon, where it just means like carbon 12, meaning that technically this would weigh just 12 grams. Okay, and that's because it has 6 protons, and you probably guess you have to subtract the 12 from the 6, and that's the amount of neutrons you'd have. So to have this carbon will have 6 protons, 6 neutrons. Okay, but there are also carbons running around nature that are like 13.6. Okay, still carbon, right? But now it has 6 protons, 7 neutrons, and this 13 here relative to that 12 there means that this carbon actually weighs around 13 grams. Now these are just carbons that do appear in nature, okay, but in terms of now to calculate atomic mass, right, they appear in percentages. So let's say out of the 100% of carbons out there, the reason you have a number so close to 12 is because typically you see like around 90, a really high number, 96, 98, something like that. 98% of carbons are the 12.6, and like 2% of the carbons are 13.6. So the way you calculate the atomic mass unit is by getting this mass here and multiplying it by the percentage that shows up. because it's pretty much saying now that the 12 grams accounts for 98% of all the carbons out there, and the 13 grams counts for like the 2% there. And you notice that you end up getting a number that's a little bit greater than 12. So like in this example here, I'm using 98 and 2, so it'd be like 12 grams times 0.98 plus 13 grams times 0.02, because remember, this is percentages, so it's going to be whatever number you get divided by 100, which is why we have 0.98 and 0.02. When I put that in my calculator, plus 13 times 0.02, you actually get 12.02. That is how they actually got the atomic mass. So when you see these numbers on your periodic table, that is actually all the recorded common isotopes of that element added together in these percentages based on the percentage of how much they account for. Okay, and that's how they get their actual atomic mass you see on the periodic table. So that would be how you calculate it. As they see here, they actually use what's been shown like on record, like the empirical data, and there's exactly a lot close to like almost 99% of carbon 12. I mean, of carbon is carbon 12, and only the 1% is that stranger carbon 13. And think of it this way: there are actually different types of isotopes as well, like even maybe carbon 14 or carbon 11, like those really rare ones. Only the ones that they actually shown that can actually exist. But the point being though is that they're like less than 0.1%. For example, they account for so little of it that it barely changes or even doesn't change the atomic mass of that element. When you get to bigger elements like uranium and stuff, for example, they have a lot of isotopes, very unstable isotopes, but nonetheless still there. And because they're there, they're factored in, but the percentage of how they exist in nature makes them not affect the total atomic mass as much. But yeah, so this is correct. So let's submit that. Now let's move on to question 6 now. So now this one's asking, is HCH3CO2 a strong or weak acid or base? That's actually a great question. So we have CH3COOH. I prefer to write it like that because it actually helps me see it a lot better. And now that I know it's that, this is actually just acetic acid. So with that being said though, let's actually focus on the question at hand here and make sure we actually have the right molecule. So 2 C's, H3 here, and H at the end, and 2 O's. Okay, so we do have the right one here. And is it a strong or weak acid or base? So with this, we first need to write out our dissociation formula. CH3COOH. Okay, and we actually only know that because we have to actually draw it out. I would actually start with that first. Sorry about that. So CH3COOH, for example, right, would actually be like this right here is acetic acid. Now the reason why I actually drew it is because you notice that how it's positioned, right? These carbons with the hydrogens, okay, they don't interact with the as in these are not the hydrogens that are given away. It's actually here with this resonance structure, well, soon to be resonance structure, is where the hydrogens leave. So this hydrogen here, okay, I'm gonna circle it a lot, is the one that gets out. Okay, that's the, in a sense, the acid complex of CH3COOH, allowing this to form a resonance structure as I mentioned earlier. Point being though, okay, is that so if we were to write this formula in terms of the dissociation formula, right, it'd be this, okay, double arrow, okay, CH3COO minus plus H plus, okay. So with that being said, okay, based on that, we can say, because it's actually given a hydrogen, this is now defined as an acid, okay, making this its conjugate base. When the hydrogen is in the product side, that typically means that it's being given away, okay, making, at least in your half reaction, okay, making that molecule an acid, okay. So that's an acid with its conjugate base. So at least now we can say that it's an acid. Let's just write it down here, okay. And now we need to know whether it's a strong or weak acid. So face value, I'm going to tell you honestly, you cannot determine whether it's a strong or weak acid unless you've just memorized the list of strong acids. The good news is that there aren't many, but that's just the unfortunate trick to it. The other way to know whether it's a strong or weak acid is that if you haven't memorized a list of strong and weak acids in your head, hopefully you've been given a Ka table, which is a dissociation table. Well, actually it's just going to be K, but Ka is for acids, so dissociation for acids. Okay, now for Ka, the greater the Ka, okay, the stronger it is at dissociating, as in like separating, making it a stronger acid because it's able to, in a sense, form more of, I guess in this case, the hydronium, okay. The greater the Ka, the greater this thing splits apart, okay, and because it's splitting apart, there's more protons floating in the solution, okay. And we actually have barriers of how we figure that out. For Kas that are between 0 and 1, okay, these are what you consider weak, okay, relatively weak acids. And then for any Ka greater than 1, this is what you define as a strong acid. So we have now two barriers for what we are looking for in terms of the Ka. And hopefully you were given an actual sheet, okay, and we go over to our acid sheet here. We're looking for acetic acid, okay. So CH3COOH, there we go, acetic acid. What is this Ka? It's 1.76 times 10 to the negative 5, okay. And you can already kind of see the answer here. Anything greater than 1 right now just says strong acids. That's all you need to know, okay. So with that being said though, this number, is this greater than 1 or between 0 and 1? Making sure you pay attention to that exponential factor, 10 to the 10 to the negative 5, you will know that this is between 0 and 1. So with that being said, because this is the Ka of acetic acid, this is a weak acid, okay. So that is your answer there, okay. And just as a disclaimer, you will never or should never get a Ka that's less than 0 into the negatives, because it doesn't make sense for I guess molecule to become even less dissolved. That makes sense. If you start out with a solid, you don't get more solid by putting it in a solution that has nothing but water. It needs actual constituents to be able to form itself back. But point being is that exactly, you won't get a Ka less than 0, and you need that to find out if it's a strong or weak acid. You can use a formula to find whether or not it's an acid or base, but you need your K values to actually know if it's strong or weak. Okay? Yeah. So yeah, this is correct. Actually, there is something, let me see, the smaller the value, the stronger the acid or base is. Yes, exactly. So they're talking about pKa and pKb. So that's just, it's almost like Ka, but it's negative log Ka is equal to pKa. And pKa is kind of like the pH. The lower it is, the closer you get to 0, the stronger the acid. But yeah, So this is correct. Now let's move on to question number 7. What is an ionic compound? Ooh, we did touch on this a little bit, but just to really elaborate again, an ionic compound can be simply broken down. Okay, I'm gonna put a little question mark there, as in what is it? So an ionic compound is a metal and non-metal, and it just needs one of each, at least one of each, because as we saw actually with yeah, exactly, the sodium hydroxide, that's an ionic compound. What if we had sodium acetate? Okay, that's sodium acetate. This is still an ionic compound. Why? Because we remember how we did it. We still split it. Okay, and when you split it like that, right, what you've done now really is assigned a metal part and a non-metal part. Because if you go through CH3COO, right, okay, that is really just hydrogen is a non-metal, carbon is also a non-metal, and oxygen are non-metal. So everything here is non-metal. Okay, and then the metal side, all we have is sodium. Okay, so that is really how you distinguish an ionic compound. But now the question is, you know, what if you have like ruthenium? Actually, I don't know how that one bonds. Let's say you had Fe2O3, okay, iron oxide. Is this an ionic compound? Well, you have to look at the periodic table for that, and these are the kind of things you have to memorize. When you highlight over iron, right? In fact, if you highlight over this part, it actually says what it is. These are transition metals. So these still count actually as metals. And so now you still have your metal and your non-metal, making this an ionic compound. Okay? And there are a few more trickier metals you have to get used to, like aluminum, for example. That is still considered a metal, even though it's all the way on the 13th column. Okay? You'll notice that there's a lot more metals typically than non-metals on the periodic table, but it's just very important that you know which the non-metals are to be able to say whether it's an ionic compound or not. And I would say the best thing to do is just get familiar with the periodic table and know what's a cutoff for each type of non-metal, so that way you don't accidentally assign like something to the wrong place, you know. So these here are the non-metals you're typically looking for, okay? And these ones, so alkaline metals, alkaline earth metals, transition metals, post-transition metals, these are the kind of metals you're looking for as well to be able to say it's an ionic compound. Okay? Yep. And they just talk more in this question about how they work. So an ionic compound, typically the way it's officially drawn is that when it's an ionic compound, let's actually use the iron, let's actually use something simple like sodium. When you draw the Lewis dot diagram, right, okay, it'd actually be like this. You would think that, let me actually draw it first like that. You'd think that they would share, right, like that, where they have like kind of a bond there. But because metals, they can just in a sense shed away their electron, they can fully in a sense donate the electron over to the non-metal, it'd actually be kind of more like this. So we have our negative, okay, and our positive. So if I have to actually space it out, it'd be like that, NaCl minus, whoops, that's supposed to be inside, sorry about that, it's supposed to be on the outside, so you don't confuse it with the, so you see Cl minus right there and Na plus. Okay, this would actually be the Lewis diagram. You notice that the sodium and the chloride are kind of completely separated because it's just giving this electron. They're not really sharing it like you'd see in like water, or even better like CH4. These ones all share it in a covalent bond. It's not going to be drawn like that. You'd still have C H H H H like that, and the whole thing would be together. Okay, but this is how you would do the Lewis diagram for ionic compounds, because they've given that electron completely to their non-metal part. Okay. So let's move on to question 8. All right. What is the molecular formula of aluminum sulfate? That's definitely a great question here. So first we need to find out what aluminum sulfate is. So first, molecular. So similar to what we did before, we kind of have to deconstruct and figure out what aluminum sulfate is. And we discussed this earlier where we separate like that, just kind of somewhere in the middle here. So aluminum sulfate. So now let's use the easier part. We know that aluminum is just straight from the periodic table, aluminum. Now sulfate, okay, this is different. If it was aluminum sulfide, okay, it'd just be the sulfur. But sulfate, these are the things you have to memorize as well. There's like sulfate, chromate, phosphate. It's sulfur with a certain amount of oxygens. The amount of oxygens are something that you also have to memorize and get familiar with. Specifically for sulfate, that's SO4, okay? And sulfate, okay, the SO4 actually has negativity of 2-, okay? So SO4 2-, okay? That is for sulfate. Now aluminum, that one, to figure out the amount of valence electrons it has, as I said, the typical way for the easier metals and elements in general is to just go with the periodic table. So it's on the 13th column. So you expect it to have 3 valence electrons, meaning it wants to give away 3 of them, all 3. Alright, and if you wanted to use a different method of electron configuration, you'd actually have neon. Okay, that's what you start with. Alright, and then you'd have 3s2, 3p1, okay? And that 2 and 1 is how you know that on the third most outer shell for aluminum, the third shell, there's 3 electrons in total. And they'd rather give away those 3 than to go through the hassle of trying to add 5 more. So now we want to balance out the aluminum and the sulfate. How are we going to do that? So we look at these numbers. We need to find their lowest multiple that has both 3 and 2 in it. The only thing there that can do that is 6. Because you can't use 3 because it doesn't divide evenly in 2. So you need 6 for both. So you get to 6 from aluminum, you need to be times 2. And for sulfur to get there, it needs to be times 3. Okay? Because the goal here is that you still want a net electronegativity of 0. This should cancel out. 6 minus 6 equals 0. So with that being said, you have Al2, okay, SO4, 3. That right there is aluminum sulfate. Now, as you can see, Lance, we would have never gotten this and would have definitely, probably puts the wrong values in different places. So let's see how we did though. Yep. The molecular formula for aluminum sulfate is Al2, SO4, 3. So this is correct. Okay. And exactly, as we solved it, we really broke it down. We figured out how many electrons aluminum likes to have. Sulfate is something you do have to memorize. It's a little bit unfair for me because I kind of just said that's what it was. But it's actually, you should have a list of them, especially when you're in the level where you start dealing with all these 8s. These are something that you need to memorize because there's a lot of them, but as you see them more and more and more, you get used to them. Okay. Sulfate's a very common one as well. You see sulfate, phosphate, typically those two. Okay. Now, for question 9, it's asking us a conversion factor. So surprisingly, actually, I would actually equate this to kind of just working with when we did the gallons to liters the gallons to quarts, or is it quarts to liters? Point being is that it's a similar fashion to where you just want to keep your units. So this question is saying we want to go from torr to kPa. So right now we know we're starting with X amount of torr. Okay. So like we did for the other question, we just go directly to our conversion sheet, and hopefully it has it there. Do I have pressure? Yes, I do. Perfect. Do they have torr? That's a little bit frustrating. Maybe physics might have it. So that's why I have 2 of these tables open, because exactly there's a lot of units to keep track of. So hopefully we can see it here in pressure. Oh no. Let me see here. Maybe in the chemistry constants. Nope, it's not. These aren't constants. So let's just try to search it up then. Different ATM conversion. Oh no, different pressure conversion units. Okay. And there we go. Nicely done. Oh. So torr. No wonder. So we technically do have it, but it's in a different name. Okay. Right there. So we actually need to do 2 steps for this one actually, because now we know based on what it's saying here, okay, and something that I think it's better for us to just memorize is that a torr is also the other name for millimeters of mercury. So for this question here, actually, it'd be X torr is equal to, we want to go from, sorry, not equals, we want to multiply. I want to turn the torr to the millimeters of mercury, so it'd be easier for us. So we want to make sure we get the torr out, so it's in our denominator, and 1 millimeter of mercury. Okay, so now that we've done that, okay, we can actually now work through the rest of the question. So it says that 760 millimeters of mercury is equal to 1 ATM. We're going to do multiple steps here just to really get this question. And now we have ATM. We're going to go from ATM to kilopascals. Okay, so that is 1 ATM is equal to 101.325 kilopascals. Okay, so now when we try to cancel our units, hopefully you'll see that everything leads to kilopascals. So the answer for this would be that we have to get the X, divide by 760, and multiply by 101.325. 325 divided by 760. So X, okay, every torr that you get, it'll be 0.13, and we're just gonna round there. Okay, 0.133, I guess, because yeah, 0.133x of kilopascals. So no matter what value you have when you plug it in from torr to kilopascals, let's say we had 1,000 torr. Okay, if you multiply that by the 0.133, that would be that you have 133 kilopascals that you're dealing with. Okay, and now let's see, based on this answer, okay, exactly, X divided by 760 times 101.325, okay? And exactly, you do get that 0.133. You can check it as well on your calculator just to make sure. But exactly, that would be how you solve this question here. Now let's move on to question 10, okay? All right. So this question here is asking, what is a chemical formula for hydrogen oxide? So, chemical formula for hydrogen oxide. So, this actually would not even, this doesn't exist as a, based on the naming rules, the nomenclature rules actually. Hydrogen oxide is not a real name that you can use. Sorry, I just want to mention this discharging. Yeah, because the rule is actually, okay, let's look at the periodic table. What's hydrogen? This is a non-metal, and oxide just stands for oxygen really. That's also non-metal. Based on the proper naming rules, okay, hydrogen, that hydrogen part needs to indicate how many hydrogens there are. Even if there's only one, what you should see is monohydrogen oxide, okay? That at least is what you should be seeing. Hydrogen oxide, not a real even like name for it. And monohydrogen oxide, although it doesn't exist, it kind of just be OH, okay? And I mentioned this is because you need this part. You cannot drop it in the proper naming rules when you're dealing with nonmetals. For ionic compounds, yes, you can just say, you don't say monosodium chloride, you just say sodium chloride. But when it comes to two nonmetals, so covalent bonds, covalent molecules, you have to state how many they are in the beginning, the first element. So with that being said, actually, if someone said not monohydrogen oxide, someone said something a lot more familiar. They said dihydrogen oxide. Okay. That, okay, would actually be what we know as H2O. Okay. That is actually that hydrogen oxide. And now there's one special one. I know I just said the whole rule of, you know, hydrogen has to be named, but if you said hydrogen peroxide, so this is one of those okay, special cases. Okay, peroxide means that, so oxygen typically nature likes to run around in O2, right? Okay, but peroxide is when you take half of that. So you really just have one oxygen, and exactly one hydrogen. But here's where it gets complicated. That's not how it shows up. Although it has that name here, which is what you would want to put, you would think it's like monohydrogen oxide. Hydrogen peroxide is H2O2. Technically, yes, it still has that whole half of the oxygen, because typically it'd want to be, you know, the H2O. That's this much stable form. It will look like that. Sorry, it will look like this. That's water. But hydrogen peroxide says, no, I'm not going to do that. It's just a completely different molecule. So that is hydrogen peroxide. In regards to just an hydrogen oxide, that's something that doesn't really exist, as I stated. You definitely need to designate it. Hydrogen peroxide definitely breaks even the rule that I stated earlier, but I'm guessing it gets a pass because at least the second element actually has a quantity next to it. So exactly, this one says dihydrogen monoxide. Water is usually the name that's used. If I remember correctly, It seems that they want you to be able to name as in include both. So maybe the case is that you actually want to label how many of your second element you have. But either way, if you don't have the prefix, this right here, hydrogen oxide, just is not a thing, unfortunately. So for this one, I would definitely review the answers to the nomenclature. I believe it's just that you need the one in the front, but there's a high possibility that for covalent compounds, you need both indicators. They need to indicate how many of each one you have, okay? But then again, it raises the question of why hydrogen doesn't say monohydrogen peroxide. So definitely something to contemplate in regards to these type of questions. But with that, let's move on to question 11 here. Okay. Now let's see here. Just a quick water break here. So, this is asking us, what is the molar mass of silver nitrate AgNO3? So, molar mass of AgNO3. Okay, so with this being said, okay, let's think about this. It is relatively straightforward because all we're dealing with is now just going straight to our periodic table. So like we've been doing, and we'll keep practicing this because this is very important for chemistry, you want to count first your constituents. We have 1 silver, 1 nitrogen, and 3 oxygen, okay? And NO3, even though, as we were discussing earlier, just trying to tie everything together, this is an ionic compound. NO3 is the non-metal side, but it's mixed of, different constituents. It's not just one giant element called NO, okay? So with that being said, let's now do our multiplication. Okay. And Ag, silver, is 107.87. Okay. Nitrogen is 14.007. Oxygen is 15.999. Now let's make it equal. So actually tying things back, for example, silver has isotopes that are around this general number, and it's actually you find a percentage of each isotope, and that's how they got 107.87. Same with nitrogen, and same with oxygen. 47.997. Okay, plus 14.007 plus 107.87. Okay, 169.874 grams per mole. And that right there is your molar mass of silver nitrate. Okay. 169.874, 169.88. So this, for these type of questions, I just kind of check what they say for the answer, because exactly, as long as they have the same answer, it means that they kind of went through the similar steps. You can see here they multiply 16 by 3, which is what we did, and they made sure first they had the atomic mass of each element. Okay. So with that being said, this is correct. And now let's move on to question 12. Oops, I like to keep my colors consistent. What is a formula mass of nitric acid? So, nitric acid, not sure if you have the time, maybe you already paused it and found the answer already, but nitric acid Now this is actually one of the more complicated ones because you kind of have to know two things off the bat. So for acids, you know that there's an H, okay? At least one hydrogen. That is like the acid component, okay? And now we want to be able to know what nitric acid is. So there's the hydrogen. Now here's the part you have to memorize, is that certain types of certain types of elements combine with oxygen. When you turn to acid, they end in ic. That's a very long explanation, but let's put it this way, okay? If it's an acid, in fact, let me just put it this way. Acid, right? So then we have IC is the end, okay? No acid, as in, just by itself, it ends in 8, okay? So the reason why I say that is because we're actually going to tie way back to what we were doing. Remember when I mentioned sulfate? In this case here, nitric acid started off as a nitrate, okay? This is nitrate, NO3 minus. As I mentioned, for nitric acid, you need at least one hydrogen because they come in pluses, just like 1 plus. So to balance this out, you have 1 plus and 1 minus. So nitric acid is just HNO3. Now, the thing is though, is I was able to just, say that because I've gotten quite familiar with these type of molecules, but there's like nitrous as well, like nitrous acid, which is NO2, okay, and instead of 8 being like that's nitrite. So just like things like that you have to memorize, and like this one will be considered the full one, and this one will be like -1 oxygen, okay. And as an example, we have NO3, that's the 8, and NO2, that's an 8. But I'm probably just like spouting a bunch of almost nonsense, which is why for these it's just important that when you are given the table with the different sulfates, different types of 8s, and then the different types of ions are on that list, it's just very important to get as familiar as you can with them, because especially in chemistry, these things don't just show up and disappear. They're quite reoccurring. So just to have the best foot in chemistry is always just to be able to kind of get familiar and start memorizing them as early as possible, because you will thank yourself later for sure. So that's HNO3, that's nitric acid, but that's not what the question is asking for. It's asking for the formula mass of nitric acid. So there's a part 2 of this. Now that we have the actual molecular compound nitric acid, right, the formula, right, we need to now get its mass. And we do this the same way. 1 hydrogen, 1 nitrogen, 3 oxygens, okay? And now we know that oxygen was 15.999, 14.007, 1.008. I just remember exactly. We've done quite a bit of questions, so if you've listened to these videos, you also start getting real familiar with these values and just be able to just say them right off your top of your head. 1.008. But I would actually preface that with, it's never too much of an effort to check what you're saying is correct. You don't want to be using the wrong numbers and then getting to an answer you do not recognize. Okay? So now we're going to add all this 3 together. Plus 14.007 plus 1.008, 63.012 grams per mole. That is a molar mass of nitric acid. Okay, and let's see how we did. Nice. Amazing. So first, they just say that the chemical formula is HNO3. But I kind of try to break it down, but it still really just goes down to just memorizing that concept. Unfortunately, I cannot just give you a way for you to just get it right off the bat. it is something that does take practice, unfortunately. So I definitely implore you to continue trying to memorize that table and stuff. But the best way to memorize is just to do questions, and that way, you know, it gets more and more familiar. So with that, let's move on to question 13. How do you find the molar mass of argon? Okay. So molar mass of argon. Okay. So for this one, actually, just wanted to get up and, you know, get a bit more comfortable. Okay. This, we need to recognize what type of element it is. And honestly, actually, for some reason, we're already there. As it already says, argon is a noble gas. The reason why this is important is because when you deal with a lot of gases, I can name a few off the head: nitrogen, hydrogen, oxygen, fluorine. These are all types of gases typically in their normal state, in usually like room temperature. And you notice actually that most of these come in pairs, like that. That's how it's stable. Okay. Noble gases are gases where their valence shell is full, and these type of gases don't need to come in pairs. They actually just float by itself, just like that. This right here is argon. That's literally what type of I guess elements / molecules you see floating around. It's more so an element because exactly like it doesn't have any other parts for it to be really called a molecule. It's just a singular element. So in a sense, this is actually a trick question, because the molar mass of argon would really just be the atomic mass of argon. So if you see there at 39.948 grams per mole, this right here actually is a molar mass as well, because of the fact that argon is just an element of its own. Full shells don't need to accompany by anyone. That's actually how you find it. So exactly, first you find out periodic table, recognize it's a noble gas so you don't accidentally make it like Ar2. That's not something you want. Okay, and then based on the fact it's a noble gas, you can just use the atomic mass as its molar mass. The thing of it just is kind of like supporting your answer. So let's see what they say here. Exactly, they're pointing at the atomic weight, and they just say that based on the atomic weight, that's the molar mass of argon. The trick here is really just knowing that it's a noble gas. Oops, don't know what I did there. So this is correct. Okay, now let's move on to question 14. Okay. What is the definition of a polar covalent bond? Ooh, now this is a doozy of a question, because there are many ways to define it. Okay. For example, let's give a visual example. Okay. NH3. Okay. Actually, that's not even the right thing. I wouldn't even mention that actually, because that's almost unrelated. There are ways to make non-polar bonds but still have a polar molecule, if that makes sense. But thinking about it, there's also ways to make polar bonds and have a non-polar molecule, because polarity usually indicates direction. So let's actually write the question down first. Definition of a polar covalent bond. Okay, so now the way this works, okay, this is gonna be might be a little rusty just because it's been a while since I did this, but there's different ways to break down what type of bond you have, and you find that out based on electronegativity. So electronegativity difference is how you find out if polar or non-polar. Okay, and you're probably wondering, what is electronegativity? You should have a sheet as well, because some periodic tables don't include it. But if we hover over these elements, for example, right, hydrogen, let's start there. You see this has an electronegativity of 2.20. I don't know what that's doing. Oh, that actually shows the electronegativity. Okay, there we go. So let's actually switch over to electronegativity. That's actually perfect, because it's actually on a, exactly, it has, right now it's showing logarithmic. This is more linear. The point being is that if you had your periodic table, so mind my drawing here, and just scroll down more because we're on question 14. Actually, you know what? I don't want to show the borders. So we had the periodic table. Okay, that's kind of the periodic table. That's a pretty good picture. The electronegativity increases in this fashion of a, I guess, trend. This is how it trends. The lowest electronegativity thing is right here. Okay, this is the element here, and this is francium. And the highest electronegativity is actually going to be chlorine, I believe, or fluorine. Yes, fluorine's at the top. So here is like around here, and that's fluorine. Okay, we don't really count the noble gases really. These ones can be ignored, and we also don't really factor in. I mean, kind of we do factor in hydrogen, but typically we don't really factor in the noble gases, which is why fluorine is the highest one and not like neon. So let me actually just redraw that. So fluorine is like up, oops. This is fluorine in this corner. Okay, the topmost thing, and francium is the bottommost thing on that end. Point being is that this is the electronegativity I guess relationship. It increases that way. Just remember that, okay? If you ever think of electronegativity, just think of a big arrow going that way, okay? So with that being said, this is the directionality of electronegativity. Now, how does that actually let us know about a polar covalent bond? There's ratios, okay? If the difference between them is between 0 to 0.3, okay, this is considered a non-polar covalent bond. Okay, if it's now between if it's between 0.3 and 1.6, this is a polar covalent bond. And if it's typically it's above 2.0 and greater, so greater than 2.0, that's an ionic bond. Okay, and now you're probably wondering, okay, so what happens between 1.6 and 2? So it's not a rule set in stone, okay, even for the 2. Pretty much is that if you have metal and non-metal, it's ionic. As we discussed, ionic bond is metal and non-metal bonded together. But there are some strange situations where you have a value that's still greater than 2.0, but it's still going to be a polar covalent bond because it's still 2 non-metals. So just make sure you're always checking whether the actual elements together are, metal or non-metal. Now, with all that being said, okay, let's look at, for example, if we want a polar bond, right? Let's say we had CCl4. Because remember how I mentioned how, well, briefly, that you can have polar bonds but a non-polar element, okay? Because there's different things, right? CCl4, every chlorine to carbon, right? You have that 3.16 minus 2.55. It's not the biggest difference, but it's enough, right? 0.61. Technically, that is a polar covalent bond. There is polarity. The chlorine tends to be more negative and the carbon tends to be more positive. But if we were to draw this out, actually, we'd have a perfect, oops, sorry. Okay. A perfect tetracarbon. Well, I mean, exactly. A tetra structure. Okay. And this, because actually there is equal pull in every direction. Okay. And remember that this is a 3D structure. So in this 3D plane, is like there's an equal pull in every direction. This is a non-polar I'm really blanking out, non-polar molecule. Okay, I'm just going ahead to try to explain, because just because you have polar bonds does not mean you have a polar molecule, and vice versa. I'm actually going to show you now an example of something that has non-polar bonds but still a polar molecule. So let's think of nitrogen. Is nitrogen a good example? No. Let's see. If we did, cause that's really just on the borderline there. Let's try it though. Let's say if we had, it's right there in the bond, in the but NO2. Okay, nitrogen dioxide. Is that actually a bond? No. There has to be an easier one we can use. Is it boron 2.4? Yep, there we go. No, but that's also non-polar. Interesting. We'll definitely figure one out, because I'm thinking like if we get nitrogen dioxide, yeah, actually that could work. Well, then it's not an equal distribution of bonds, so guess we'll never know. The point being is that if we had NH3, right, the reason why I didn't want to use H is because H is all the way at 2.20, so these are already polar bonds. The key here is that it has a lone pair, which makes this like skyrocket up, as in like towards the lone pair. So this is a polar molecule, okay, and as you see here, it definitely also has polar bonds, because I couldn't think of an example where it would be non-polar, but exactly so. The thing is that nitrogen is 3.04 minus 2.20, which is like 0.84. So exactly, it still falls in the range of a polar covalent bond. Okay, so it has polar covalent bonds and it's also polar because of that lone pair. Maybe next time I'll come up with actual something that, you know, would count as, oh, maybe sulfur. Nope, fluoride is too strong. So with that being said, overall, to define a polar covalent bond, and the key word is bond, this is the limit right here. Oops, don't know how that happened. Let's just do this real quick. There we go. So 0.3 to 1.6, that is what you would define a polar covalent bond, and that is from your electronegativity. Okay, so I know they mentioned just like water, for example, but you see, they're actually trying to say That is right though, as in it is a polar molecule, but that does not determine whether it's a polar covalent bond. What you need to do there is find the electronegativity of oxygen, which is 3.44 minus 2.20. Okay, 1.24. Because there's a difference of 1.24, that falls in our range here of 0.3 to 1.6. Okay, which is why we can say that yes, water has polar covalent bonds. It's not just from this, it's from the electronegativity. So I'm going to say this is incorrect because you need to use electronegativity to determine polar bond or not. Polar covalent. Exactly. I can't really say it's correct because they're looking at the wrong thing here, okay? So, with that being said, let's move on to question 15. Oopsie. What are conjugate acid-base pairs? So actually, the best way to actually write this out is just by writing a generalized formula, okay? And this formula I like to think of, okay? HA, actually let me just write the question first. What are conjugate acid base pairs? Okay, so with that being said, okay, I like personally to just use this formula, okay? HA, so it's H with some, I guess, molecule attached to it, the hydrogen plus that, okay, dissociates to A minus plus H plus, okay? This is the formula I like to use right here. Very crucial. Most acid base, if not all, interactions can be broken down to the formula like this, okay? This is the conjugate acid. This is the conjugate base, okay? So if I were to just write this outside so we can read it a little bit easier, okay? The reason being is because the conjugate acid is the molecule that still has the H, okay? So that is a conjugate acid. The conjugate base is the same molecule, but now it's missing that hydrogen, okay? So let's see what they say here in regards to it, just to make sure that we're on the right track at least. Talk more about the Bronsted-Lowry acids and bases and stuff in terms of giving the proton and taking the proton. If you look at this formula, when this acid goes over to the product side, you will see that it lost a proton. That's how you also know this is the acid, because when you track through this equation, right, it goes from 1 to 2 things, okay? It is now thrown or given away that proton. Now if you take this reaction backwards, you see 2 things become 1. This base has snatched a proton to become back into its proper form, okay, making that the conjugate base. An example that we actually saw earlier of a conjugate acid slash base pair is actually our favorites, CH3COOH and CH3COO minus. So if I were to ask you which is a conjugate acid and conjugate base, you should be able to notice first which one has a hydrogen to give away. And remember we discussed that these hydrogens here don't count, okay? So based on that, okay, the only one that can give away hydrogen is this acetic acid is what it's called. So with that being said, this is the conjugate acid. And exactly, this CH3COO minus, which is the acetate ion, this is a conjugate base. This would be the basic part of it. This would be the acidic part of it. And as a bonus, actually, if you ever look to build buffer solutions, that's actually what you use. Not acetic acid specifically, but you want the H want a ratio of some ratio of HA and A minus. That is how you actually make a buffer solution. And I mentioned it this way because, for example, if you had let's see, exactly like CH3 COOH, and then you also had NH4 plus, this is not going to make a buffer solution because, for one, these are both acids, and two, they're not even like their conjugate pairs. Even if I put NH3, now ammonia is actually a base, but this wouldn't make a proper buffer solution because of the fact that these are two different types of molecules. NH3 is not acetic acid conjugate base pair, okay? And that is what we're looking for here. NH3's base pair is NH4, and so that's that right there, okay? So it's just important that if you ever want to make buffer solutions, you're not just grabbing any weak acid and a weak base. You need the weak acid and its conjugate base, just as how we've described here, okay? So exactly, they mentioned it. HCl and NH3 react. Exactly, NH4 is the conjugate base for NH4 is a conjugate acid for NH3 minus, and in this case, HCl is a conjugate acid and Cl minus is a conjugate base. But that one can't be used to make buffer solutions because hydrogen chloride, I feel like I'm saying that wrong. Hydrochloric acid, there we go. Hydrochloric acid is a strong acid, and so when it dissociates completely, so there's not really, you can't make a buffer solution out of that. You can't add salt and hydrochloric acid. You can't really add those two together to form a buffer solution. You need weak acids to be able to form that buffer solution. But that's something we'll discuss later on in the future into more depth and detail. Point being is that for conjugate acid-base pairs, it's the HA, which is the hydrogen plus the ion, and then it goes to form the ion and the hydrogen separately. That is a conjugate acid-base pair. Okay, so let's go on to question 16. Okay. What is the formula for hydrosulfuric acid? So, formula for hydrosulfuric acid. So I like how actually everything connects, because when I said HCl, right, like hydrochloric acid, I said exactly hydrochloric acid. I said that this is hydrochloric acid. So using that same logic, okay, if we have hydrosulfuric acid, we know now we have a sulfur, okay, just a sulfur. This isn't this isn't sulfuric acid, okay, or what am I trying to think of? Phosphate forms into phosphoric acid. Exactly, no, we're on the right track. And exactly, when we scroll back to earlier questions, when we're talking about nitric acid, for example, it's not the same thing as hydronitrous acid, which I don't really ever see. Point being is that, to get back on track, it's just sulfur by itself. Hydrosulfuric acid, it's sulfur by itself. Now we need to figure out actually, and also hydro. Okay, we know that it has a hydrogen. Okay, but what we do not know here actually is specifically. Sorry, I'm gonna keep messing with my charger. We don't know how many hydrogens or how many sulfurs we need. We know hydrogen has only one electron giveaway because you know, it's 1s1. That's hydrogen when you write an electron configuration. For sulfur, okay, it's, you just start a neon, okay, and it's 2, don't I keep putting 2, 3s2, okay, 3p4, and these two numbers 2 and 4 let us know that its valence shell is 6 electrons. Now I can say without a doubt, for most things, even in nature, it's easier to add when there's a less step than to subtract when there's a bigger step, meaning that you want to follow the octet rule, so you either want to have 8 or nothing. Sulfur only needs 2 more to get to 8, so it really just likes to take 2 electrons. So with that being said, sulfur is typically 2 minus, okay, and hydrogen is 1 plus, as we discussed with the 1s1, okay. So with that being said, to balance it out, we need to multiply our hydrogen by 2. So hydrosulfuric acid will end up being H2S. This is hydrosulfuric acid. But I did use a hydrochloric example to answer that. But what if we were given another name, as the question also asked? Dihydrogen sulfide, which is technically the name they have to give because of the fact that when you notice on the periodic table, hydrogen is a non-metal and sulfur is also a non-metal. So based on the naming rules, 2 non-metals, you need that indicator, the di in front of it, okay? You know for a fact it is not ionic compound. So with that being said, we just follow what it says here. Dihydrogen, di means 2, and sulfide is just sulfur, just one of them. So we get the same answer here as these two, okay? It's just that it depends on what you know in your background. Exactly. They were quite gracious to give us the dihydrogen sulfide, because if they hadn't give us that clue, you kind of had to infer how hydrosulfuric acid worked based on hydrochloric acid and hydrofluoric acid as well, like HF, because that's really, for me, actually the only way I would have figured out that hydrosulfuric had no like oxygens with it, like it wasn't sulfuric acid. Okay, so exactly talking about what di means. In this case, you know, it means 2, and exactly, and they mentioned how exactly if it ends in ide, IDE, when you're naming it, that's just how it ends. But exactly, this means that you're dealing with only the elements. You're not dealing with like a more complicated compound. Okay, and then exactly, and they mentioned that using the guide above, they kind of reverse engineered it and got H2S. So this is correct. Okay. And now, let's move on to question 17. What is the electron domain and molecular geometry of BrO2? So, electron domain and molecular geometry of BrO2 minus. So this one is actually a doozy of a question, because bromine is actually a valence electron. I mean, not a valence. It's actually a halogen. I mean, it's already almost full. It only needs one more. But let's actually break down exactly what we do, because for this, we actually do need to start with the Lewis dot diagram. And the way we figure out that is by actually, first figure out how many electrons there are that we're messing with. So bromine has 7 valence electrons based on the fact that it's on the 17th column, and also you can also show it based on its electron configuration. You end up with 4s2 4p5, which does add up to 7, the 2 and the 5. Oxygen, exactly, we know that it's a 2s2 2p4, and also it's on the 16th column, so it's 6. But again, there's 2 of them, so that's 6 times 2, that's 12. And then the minus actually is actually just going to be plus 1 more electron. So that's going to be 7 plus 12, that's 19, plus 1 equals 20. You want 20 electrons in total. So now, because bromine is actually the one that's like, I guess, single, that's one I actually put in the middle first, okay? I'm just going to say that's surrounded by 2 oxygens, okay? Now we want to make sure we fill in 20. So first let's do the double bond, the single bond here on each side. So we've accounted for 4 so far. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, luckily for us, we actually have exactly what bromine is going to be. And exactly, we counted it all. We have 8, 8, and then 2 more at the top. Okay? 2 more lone pairs. And we actually want to see if this is its favored stability. Although each one has 8 in the electrons, so bromine, as we know, exactly 7, which is the valence electrons. And now we want to subtract the lone pairs. So we have lone electrons, that's 4, plus the bonds, so that's 4 electrons in bonds, but divided by 2. So 7 minus 4 plus 6 is equal to 1. So this bromine actually in here is going to be actually plus 1. Okay? And then we do the same thing for the oxygens, but this time is 6 minus, we have here 6 plus 2 over 2. Okay, that's 7 in total, so it's minus 1. So minus 1, minus 1. You technically want to be able to get as close to 0 as possible, okay? But technically for this one, if we try to get to 0, you would unfortunately end up with very unstable elements on the side, if that makes sense. So for example, if we try to get 1 electron over here to make it 0, because exactly it would now turn into 6 minus 5 plus 2 over 2, technically it would be 0, okay? But this is now unstable. That just wouldn't work. So this, unfortunately, and I say unfortunately because you don't really see this in nature, is the most stable state for BrO2 minus, okay? And exactly, you see that 1 minus there because of the fact that when you add up the minus 1, plus 1, and minus 1, you get in total just 1 minus, okay? Now that we figured it out, let's actually draw its shape. So with that being said, you have the bromine and you have its 2 lone pairs, and you now have the oxygens with its full shells. So actually, this right here is actually what you call a bent geometry. Okay, and I believe the angle is like less than 104, something like that, around there. Let me see here, because I wrote it down somewhere. For bent shapes, the angle you'll see is going to be around there. The lone pairs actually may influence the shape a little bit, but less than 109, so not 104, 109 degrees, okay? But point being, right, actually the reason why we know it's bent, because this is actually just a much more complicated form of something that we're actually more familiar with. Water is also a bent shape, okay, because it has the 2 lone electrons floating above it, and it forms like that. This is also the bent shape. But this exactly, we have the electron domain based on the Lewis dot diagram, and we actually have now the molecular geometry as well. So it's bent. Okay? Exactly. And you need to accommodate one lone pair, at least one lone pair on the central atom bromine. Okay? If we try to do like a very strange let's see actually what happens here if we did this. If we made it a double bond, okay, because although now bromine breaks the octet rule, maybe now it will be that it's technically more stable because the negativities end up being like close to 0. We try to find out the what's that number called again? The electron. It's not an electron number, but it's not the electronegativity either. It's just the assigned number. But let's just try that same math. The bromine, exactly, it's 7 minus. So now it has still 4, but plus 3 over 6 over 2, because now there's 3 double bonds in total, and that does actually equal 0. And for oxygen, you'll see 6 minus 4 plus 4 over 2 also equals 0. So technically, if it could break the octet rule, this would actually be its possibly more stable form. If I can just move everything up, this right here could possibly be its more stable form, but at the end of the day, you still have a bent shape. Okay, so this could be a possibility. Okay, I'm not gonna just throw it out, because when you try to actually do it, it's like now you have the numbers of 0, 0, minus 1, which is something that it may actually prefer if possible. Okay, so with that being said, I'm gonna let you look at this, take a picture of it, try to find out which stability it prefers. Might have to search that one up later, because I'm actually quite curious about how this BrO2 would work in nature. Let's move on to question 18 then. Okay, and this is correct because it does mention that it's bent, but they mentioned also could be linear as well. It's just bent. But yeah, so let's move on to now question 18. Okay, which salts will be more soluble in acidic solution than in pure water? Okay, these salts are Ag2CO3. So let me just actually write that down. Which salts more soluble in acidic solution, okay, than pure water? Okay, so now with that being said, I'm actually going to write down each one, but I'm going to write down their formula of how they would break down, because it actually helps you understand the question a bit easier. So Ag2CO3, Ag 2Ag plus CO3 2 minus. Okay, and now same thing, AgClO4. Okay, all right, and that would be let's see, where is it? I'm really blanking out. Yep, there we go. Ag plus ClO4 minus PbI2 Okay, got PB plus, PB2 plus 2I minus. Okay, now for the last one, CdOH2. Okay, will turn into CD2 plus 2OH minus. Okay, so that's each one, right? And it says which of these would more solve an acidic solution actually. Okay, so acidic solution is something that has, let me put it this way, lots of H3O plus floating around. Okay, so with that being said, actually we can actually look at these equations and kind of figure out what would happen here. So if we had I guess if we think about this when we work through this question, right, you notice that each thing kind of breaks into what you consider like a base. Okay, all of these can be considered like have a basic-ish component to them. Now for this, actually we kind of have to refer back to our acids and bases. Okay, so with that being said, actually we're actually going to now, in a sense, kind of look at it backwards. The higher it is on the table, the harder time you would actually have you have a harder time interacting with acids. It doesn't really want to mess with acid anymore. It's already done. It's, yeah. So let's actually look at this table real quick. So we're actually going to look at the A minus, okay? Remember the conjugate bases. That's really what these are, okay? So CO32 minus, where does that go? Okay? Carbonic, okay? Right here. CO32 minus, that's pretty high, okay? Right now we can just say that it's a value, okay? And now ClO4, okay? Let's see where that is for this conjugate base. ClO4 minus. There's so much on this list to be able to really. There we go. That's ClO2. Oh no. Wrong part. I'm going to do it here. ClO4 minus. There we go. It's all the way up here. So with that being said, actually, because perchloric acid is so much higher up there, right now this is going to be more soluble and this is going to be less soluble than that. Okay, let's look at iodine. So hydrogen iodide, oh wow, it's even higher up in this list, hydroiodic acid. So it's going to be like number 3 right now. Okay, but OH, it's all the way at the bottom. Okay, and so that would be our new one, because remember the highest is the one close to the bottom. So that makes this 2, this makes this 3, and makes this 4. Okay, this is going to be the most, I mean not most, this OH is the one that interacts the most with the acid, because this right here of all these 4 things is the strongest base. How do we figure that out? It's because it's inverse. Okay, the weaker it is as an acid, which is what's happening here, as you go lower down the table, it's a weaker acid. The weaker it is as an acid, the stronger it is as a base. Now, why does this matter that this part is, you know, a stronger or weak base? Because we can actually use a Le Chatelier's principle, okay? And what that is that when you use up, exactly, if there's a change in amount, temperature, or pressure, there's going to be a change in the equation to directionality of which side it favors. So in this case, right, think of it this way. Of all 4 formulas, this OH is being depleted and used most to interact with the H3O. And because you're now losing product, in fact, if we could to organize this, right, it'd be 4 would be the shortest one, 3 will be a little bit longer, 2 will be a little bit longer, and one will be like very significantly. Okay, so exactly, because now we're losing a lot of product, each one will do it accordingly. The equation for the PBI2 would shift slightly over. This one will shift a little bit more. This one will shift more than that. But this would shift a lot because the OH is being depleted quite a bit because it keeps interacting with the acid in the solution. So all this roundabout way is saying that CdOH2 will be the most soluble because exactly more of its product is being used up, making the equation go towards the products, meaning that now you have less reactants, making this more soluble. Because everything here should start as solids. So because you're now consuming more solids, you're making it more soluble. So exactly, they mentioned that it's carbonate. Ion makes HCO3, which is Ag ClO4, perchloric acid, iodide, hydrogen iodide, yeah, and then the last one, cadmium hydroxide, exactly. Thus, this salt, that's what they meant to say, will be the most soluble in acidic solution. So this is correct. And exactly the way I personally solved it, although they're kind of using the they're basing it off of the acid, you can definitely do that as well. In this case, exactly as they showed, right? The weaker the acid, the better it will dissolve in an acidic solution. That makes sense, because water is the weakest acid actually on this list, okay? And hydroiodic acid is the strongest acid because they found each of their conjugate bases. That's what they did there. So exactly, they had Hi for this one, H2O, HClO4, which is also a strong acid. It's called perchloric acid, and they had HCO3 minus, which is the one we saw. Where is it? CO3 minus. I know I saw it earlier. There we go. HCO3 minus. Not this one, actually. It's going to be, there we go, carbonic here. And exactly, it's a pretty weak acid. So if this one was not here, okay, this would be our next one, which is the one that's most soluble right after. The point being is that for this question, the answer is cadmium hydroxide, okay? All right, now let's go on to question 19. Okay. What is a formula for ammonium carbonate, okay? So for this one, you kind of have to know what ammonium and what carbonate is. I know I briefly discussed in terms of actually being familiar with the eights. This is just another example of it. Carbonate is CO3, I believe, because even at this level, exactly, like there are a lot of different types of it. In fact, I'll go to the acid sheets because I know that carbonic acid is something that's there. And if I can just find carbonic acid, there we go. CO3 2 minus, exactly. So CO3 2 minus, that this right here is carbonate. Okay, the carbonate ion. So now ammonium, okay, as we discussed, ammonia is NH3. So ammonium is just an extra proton added to it, the hydrogen, and so it's NH4 plus. So to balance these out, actually, okay, we need to make sure we have the same amount of positive negatives. So we need to multiply this by 2, and now we have 2 plus and 2 minus, so it equals 0. So for this, the whole form would actually be NH4 2 CO3. This should be the balanced formula for ammonium carbonate. Yep, and that is exactly what they get. So exactly, they just say the carbon ion CO3 2 minus. something that you just kind of have to memorize, and I'll keep stressing it as you're going over your different eights, ites, and all your acids. Keep practicing, get familiar with them, and you'll have a lot easier time with these questions. Okay, and ammonia / ammonium, same thing. It's just from familiarity from solving so many questions. Okay, now number 20. What is a molar mass of C12H22O11? Now I picked this question because it really is just solving like every other question we've solved, but it's just quite big. Okay, so molar mass of C12H22O11. Okay, so how do we find that out? Okay, we actually just break it down. How many carbons we have? A whole whopping, I'm going to give myself some space this time. 12 carbons, okay? We have 22 hydrogens, 11 oxygen, okay? So we're going to have to literally multiply this by 15.999, 1.008, and 12.011. Let me just double check. Yep, that is what we have. So now, so we should get around like 144 for carbon times 12, 144.132. This would be like 22 point something. Okay, 176. And this should be kind of just like whatever 11 times 16 is, but minus 11, point 11 times 11, 175.989. So 11 times 16 is usually 176, it seems. Point being though, is that we have to now add all these together. So this is actually kind of like the easier part because it's just big numbers to deal with. So you want to make sure that the numbers at least kind of make sense, if you know what I'm saying. We have 12 carbons and 11 oxygens. Those are the biggest ones there. So that should determine most of the weight for this element. The answer we do get here is 342.297 grams per mole. Okay, so let's see, hopefully we were able to get that correct. Exactly, they got 144.12 because they have 12.01 in theirs, 22.22 because they have 1.01, that's 176. When you add it together, 342.34, and I have 2.97 because exactly, depending on your periodic table, you will get different molar masses. So as I'll keep saying, refer to the periodic table given to you by your instructor. Okay, so this is correct. Okay, so now let's go to question 21. Okay, with that, let me just take a quick water break. Hopefully you've learned quite a few tricks from this stream. So now let's solve this question, okay? So now let's see what it says. It says, what is the molar mass of helium gas in grams per mole? So, a few red flags here in terms of going to default thinking. You may be thinking, oh, gas, so helium will show up in nature like that, He2. Okay? But this is not the case at all. Always refer to your periodic table, okay? And you will see that helium is actually a noble gas. So although it's a gas, it's completely fine by itself. It may not be the octet rule, but the first shell, which can only actually take 2 electrons, is actually full. So helium is completely content being by itself. So with that being said, actually, just as how we discussed in the other question, molar mass, because we're dealing with a monoatomic particle, it's an element by itself, it actually just equal the atomic mass. Okay? So with that being said, the molar mass of helium gas would just be 4.0026 grams per mole. Okay? That is actually all you need to do for this question to find the molar mass of helium gas. Wow, that's a little bit of a rhyme. So let's see what they got. Exactly, they mentioned that's atomic, meaning that exactly it's only one element, really. Hard to really call it a molecule, but point being is that you'll just see helium by itself floating. Okay, so that's correct. Now let's go on to question 22. Okay. How do you calculate the pH of acetic acid? Great question. So, how to calculate pH of acetic acid. Okay, so with this actually we do need some information here, but the first thing we usually want to start with is finding out the formula for acetic acid in terms of how it works. So as we mentioned, because we discussed acetic acid earlier today, it goes like that: CH3COOH, and you put it in water. Okay, plus H2O L. Okay, and then it turns into CH3COO minus plus H3O plus. Okay, that is actually what you get there. Okay, so now that we have this, okay, to calculate the pH, I want to make sure we label these. This is the acid, HA. This is the conjugate base, A minus, as discussed earlier as well. And then we have the H3O, okay? The next thing you need to be able to find out actually, you know what? Even before we go there, this here, the concentration of H3O plus, that is where you find your pH, okay? Because pH is equal to negative log H3O, okay? So the concentration of hydronium ions, you use negative log of that to find the pH. That is your formula, actually, okay? So based on that, okay, you would think also all we need to do is find out how many hydronium ions we have. That's where the tricky part comes in. So the way to find that, if they said they gave you a certain concentration of acetic acid, so you started with acetic acid, you couldn't tell right away because the other value you need that's actually equally or even more important is finding that Ka value, because the full formula actually, okay, is that Ka, okay, so the dissociation constant for acetic acid is equal to the conjugate base times the hydronium ions, okay, and the concentration of each one, divided by the concentration of the acid, okay? Usually you would just have, it's the aqueous stuff on the product over the aqueous stuff on the reactants. Water is not included because it's not an aqueous thing. It's actually just what the solution is dissolved in. Well, like it's a water solution. So this is your second formula you need. Okay. Now, with these pieces, actually, if you're given the concentration of HA, all you need is a Ka to actually be able to find out the concentrations of your products. So let's actually refer to our nice acid-base table. Acetic acid, if we remember, was like kind of here. Okay, so it's 1.76 times 10 to the negative 5. Okay, but point being is that here's actual reaction incorporates something that hopefully you've at least touched on. Okay, but if you haven't, it's called an ICE table, and it stands for initial change equilibrium. The purpose of an ICE table is for you to track how much of the acid dissociates into its conjugate base and the hydronium. Okay, so for example, I would actually put here the CH3. So this is the acid, the HA OH, forming into the CH3COO minus, that's a conjugate base, and the H3O plus, that's just the hydronium. Okay, so the way this works, okay, is that let's say you're given the amount. Okay, let's call it A. Okay, we say that we have A amount of acetic acid. Okay, you don't start with anything unless it's stated otherwise. These are 0 because you're literally trying to put this acetic acid into the water solution, so you haven't seen anything dissociate yet. So now the change is that you actually going to now get plus X, plus an amount. Okay, you just don't know how much, but you just know that each of this is going to be equal to each other, because based on this equation that we have at the top, it's 1 to 1. Whenever you are gaining amount of the conjugate base, you gain the same amount of the hydronium. And based on this 1 to 1 ratio as well, you'll see that one acid turns into one conjugate base. So A, to make up for both sides, actually just losing 1x. Okay, so the equilibrium, we just have A minus X, X, and X. Now these are the concentrations. Okay, and remember we have that Ka formula right there actually. So that means Ka, which we know is at 1.76 times 10 to the negative 5. We actually have x squared, because there's two x's on top, the two products, over A minus X. And you actually just solve for X. Now, the good news is that when your concentration is at least, so when your concentration of HA, okay, is greater than 1,000 times, so at least 1,000 times bigger than Ka, your formula turns into, so like this is a formula that you use, okay, but your formula turns into this: Ka equals X squared over A. Why? Because if your concentration is so much bigger than your K value, it means that you don't dissociate much from your actual reactant side, like what you had in your acid, meaning that, risk speaking, the number doesn't change. It would be like 100 minus 0.01. The change is insignificant. You might as well just say you still have 100. That is effectively what you're doing here, because even when you solve it this way, you actually end up with an answer close to when you actually do factor it in. Now, the thing is that when you do factor it in, when you have values that are much closer, actually, you end up with a an actual quadratic equation. So it's Ka minus Ka X. I'm actually going to put So yeah, I'm gonna stick with A, but actually I'm gonna make these B. It's not much of a change, just because I don't want to confuse that with the KA. Okay. Okay. So now that we replace everything with B, it'll be KAB, KAX is equal to x squared, meaning that x squared right in quadratic form plus KAX minus KAB is equal to 0. And then you solve for, use a quadratic equation of, you know, b plus or negative b plus or minus 4, whoops, b squared minus 4ac over 2a. That's the quadratic formula you use, and in this case it would actually be, if we use the stuff there as the b and everything, it would be negative ka plus or minus the square root of ka squared plus, because you already have the KAB as negative, and it's going to be 4 times KA times B over just 2, because A was equal to 2. So what I've done effectively is kind of just broken down what you would be solving for if your numbers were close enough between concentration and the K value. Okay, that would be kind of what you do there. It sounds like a lot of gibberish right now, only because it works a lot better when we actually have values. But there's just a few things to keep track of here. Okay, most of the times you're given equations where actually the change between b and the x that it loses when it's dissociating is so insignificant, you can mostly get away with this formula here. Okay, but if you don't, if the change isn't big enough, you have to use the quadratic formula. Nonetheless though, you solve for x, okay, which was the whole goal of this. You end up getting x, and then what happens there is that now you know not only how much conjugate base you have, but more importantly how much H3O you have, hydronium. So let's take it back to the original equation we started with, and the negative log of hydronium, after finding out the x, whether it's through the quadratic equation or just square rooting, you then plug that in to the negative log of whatever, and that will give you the pH of that acetic acid. Okay, so as a quick example, okay, let's say we had 5 moles per liter of acetic acid. So 5, nice big number. Okay, if you look at it, okay, 5 versus 1.76 times 10 to negative 5, 5 divided by that 1.76 e negative 5, it's literally 20, at least 284,000 times bigger. So it's insignificant how much it's going to change. Okay, but from 5 moles per liter of acetic acid, right, we now do the formula. So we'll see here that B is what we use, so x squared. So now we have to multiply the Ka times 5. Okay, so 1.76 times 10 to the negative 5 times 5, right? Then we square root that. Okay, and we end up getting that we have a whopping 0. This is what I mean. Out of the 5 moles per liter of acetic acid, only 0.009 was produced of H3O and its conjugate base. Okay, and now we find out how the pH is by the negative log of that answer. So the pH of 5 moles per liter, so 5m concentration of acetic acid, the pH, because now that we've actually found that 0.09, which is the concentration of H3O, was actually 2.02. Well, 2.03 if we round it properly. So that's an example of how you solve for this question. Definitely a lot of steps involved. The key thing is your best friend, the ice table. Okay, I say best friends because this thing, believe when I say this now, shows up a lot when dealing with acids and bases. And acids and bases, it's a whole unit of its own. So ice tables you will definitely see a lot of. Okay, exactly, did what we did. Perfect. Exactly, and they have it here, x squared x minus x, and exactly, if we assume that the value of x is high, that's what they did here. And exactly, they just do the square roots when you multiply them together, and that is your hydronium ions and the negative log of that. So this is correct. Whew, what a question breakdown, am I right? So with that being said though, I implore you that if you were ever confused in anything I was explaining, you can always just go back to the video, take it slow, because hopefully I included every information you needed to actually solve these. So with that, question 23. Okay. Hydrochloric acid HCl reacts with solid NaOH. What are the products of the chemical reaction? So HCl reacts with NaOH. In fact, I'm actually going to just reacts with NaOH. What are the products? Okay, so for this one actually is going to be a double substitution. That's what these are called. Single substitution is when only one side is replaced, but for this one, think of it this way. So HCl plus NaOH, what does that turn into? Okay, think of it as you end up gonna it's gonna be tricky here, because it could, in a sense, you want the positive side, the Na. So actually, no, let's break it down to half reactions. Actually, that'll actually make it a lot easier. So NaOH breaks down to the positive Na plus OH minus. Remember in this case the metal and the non-metal, that's sodium hydroxide. HCl, hydrochloric acid, breaks down to H plus the positive side plus Cl minus the negative side. Okay, so to actually fill this formula, actually you're gonna actually do it as we call a double substitution. Okay, because now you want the positive to go with the negative of the other one. So this here and this is gonna react with that. Okay, so what we get here is actually NaCl. Okay, and because there's only one, we don't have to do any fancy math or balancing it out. And H and OH will actually give us H2O. So let me just quickly add that they're aqueous. You know, you can't forget that when you're writing the formulas. And water is just a liquid. Okay, but this right here, this double substitution, will be what you get when hydrochloric acid reacts with solid sodium hydroxide. You form salt and water. But trust me when I say this, you do not want to try to eat that, just because you kind of have to rely on the fact that it reacted to completion, which only truly, I guess, theoretically works when every single hydrochloric acid reacts with every single sodium hydroxide. And you don't want to take the chance of eating something that hasn't reacted fully. But yes, you would actually taste salt if you're curious. Yeah, and let's see here what they did. HCl, NaOH, exactly, NaCl plus H2O. Yep, double substitution. This is correct. So let's go on to question 24. What's the rules? Well, what are the rules? Rules of scientific notation. Okay, so the best way to explain the rules by providing examples. Okay, so the simple breakdown of scientific notation, right, is that you want to have a number, so x point something is just going to be placeholders, right, times 10 to the power of x. Okay, all these x's are just placeholders. Okay, point being, the most important part is that proper scientific notation only has one digit before the decimal. Okay, and that is, and then the digits here in the multiplication factor is based on how many digits you moved from your initial goal. So as I said, we're going to have a plethora of examples. Okay, if I had 365, okay, scientific notation is just going to be start with decimal point, move it twice. Okay, so now you know your number. Okay, it's going to be times 10 to the 2, and now you move it twice, it's 3.65. okay, so hopefully let me just give myself more space. 3.65 times 10 to the 2. This is a scientific notation for 365. Let's say I had 0.00073, okay? Alright? So with that, okay, remember you want to get it to the point where you have only one number before the decimal, okay? So 1, 2, 3, 4, okay? So it's going to be times 10 to the -4 because you moved to the right. When you move to the left, it's positive. Move to the right, it's negative. And it's going to be 7.3 times 10 to the -4. So this is the scientific notation for that, okay? So another thing we discussed as well is like significant digits. Scientific notation allows you to have a much easier time with significant digits. If you only had 2 significant digits, for example, this 3.65 would actually be 3.7 times 10 to the 2 because you round, and then 5 rounds up. So exactly. And if you said 3 significant digits for this one, okay, it'd be 7.30 because we don't know what's, it's just going to be, we assume it's a 0 after that, times 10 to the -4. Nothing changes except for the significant digits, which is just the way it counts is that it counts the number before the decimal and then every other number after the decimal. That's how you factor in significant digits. So if you had 3.7658 times 10 to the 4, okay, this is really just 5 significant digits. 5 sig digs. Okay, but now we're straight away from the original point, okay, which is just the rules of scientific notation. This is the rules of scientific notation, okay? If you have something like this, 0.4 times 10 to the 2, this is not scientific notation, okay? This is not scientific notation because it has a number before, it has no number before the decimal. So what you actually have to do is move this over 1, and then because you moved it to the right once, it's going to be -1, so it's going to be 4 times 10 to the 1, okay? Exactly. And really this number is just 40, but point being is that this would be its scientific notation because it only has one number before the decimal point. In fact, to keep it consistent, if we're using 40 and it says 2 significant digits, it'd be 4.0 times 10 to the -1, okay? So yeah, those are the rules of scientific notation. One number before the decimal, everything else is after the decimal. And if you move to the right, which is, depends on how you're watching this, my right, okay, if I'm moving towards my right, I'm actually subtracting my exponent, so I get more negative. I move towards my left, I'm getting more positive. So for example, a common one that people would talk about is 1 million, okay? This, if you actually move it, this is just 2, 3, 4. Oops. 1, 2, 3, 4, 5, 6. It'd be 1.0 because I wanted to make 2 significant digits times 10 to the 6. Okay, that is 1 million. 1 billion is 1 times 10 to the 9. Things like that, you know. And you can tell slowly that when you're dealing with like a lot of zeros, it tells you how many zeros it has. That's kind of the trick with significant digits. It tells you the zeros in front, but it doesn't work the same way backwards, like this. Okay, 1, 2, 3, 4. That is 1.0 times 10 to the negative 4. So like there's only 3 zeros, but it's 10 to the negative 4. So remember, it doesn't work the same way right off the bat backwards, okay? So that's enough of that for scientific notation. Hopefully that explains how that works for scientific notation. But we're going to now move on, see what they said. That is correct. 1.24 times 10 to the 5. If you count 1, 2, 3, 4, 5. And this 1, 2, 3, 4, 5 is 2.45 times 10 to the negative 5. So yep, this is correct. Okay. And now let's see what they have for question 25. Ooh, buffer. I'm glad we touched on this earlier. I hope you remember what I said. But let's see. This question says, which pair of compounds will form a buffer in aqueous solution? Okay. So with that being said, okay, we have these choices: HCN and NaCN, HCN and HCl, HCl and NaOH, and D, NaCN and NaOH. Okay, so as you remember, okay, buffers are made from conjugate acids and conjugate base pairs. Okay, so now if we assume that and we go through this question, we want to make sure we grab a conjugate acid, conjugate base. So with that, we have HCN. Okay, and remember, NaCN, the sodium dissociates, moves around freely, so we just have Cn minus left. HCN, Cn minus. That's his conjugate base pair, conjugate pair as it gets. So this one actually works. So now let's look at the rest of them, okay? HCN and HCl. This one literally has HCN and HCl. That is actually 2 acids. This wouldn't even work as a buffer solution because it doesn't even have an acid and a base. HCl and NaOH, this dissociates, so OH minus. So this one, though it has HCl, it's a strong acid actually, but we're not going to touch on that yet. HCl and OH don't even match. You should have, if anything, Cl minus over there. So this is not even a acid-base pair either. And now NaCN and NaOH. Okay, so we have Cn minus and OH minus. These actually are both bases, so right away actually we kind of already get an answer, but we can't just assume yet because there's a possibility that none of them are the correct answer, although I highly doubt that's the case. The thing that we mentioned about buffers is that you need it to be weak acid, weak base pairs. Well, more importantly, one of them has to be weak, okay? As in, it has to be, not even one of them actually, it has to be weak acid base pairs. Because strong acid base dissociate completely, ruins the whole thing, okay? So let's look for hydrocyanic acid, that's how you say it. There we go. Yeah, it is hydrocyanic acid. And look at that. It is a very weak acid, if I've ever seen one, okay? But it's not so weak to where the base version, the conjugate base, is a strong base. No. It is a stronger base, but not a strong base. It's still considered a weak base, most likely. Point being here, though, is that we have now confirmed that HCN is a weak acid. So with that, we can say without a doubt that the answer is indeed A. HCN and NaCN will form a buffer solution. That is the only pair of compounds in this list that would actually do such a thing, okay? Let's move on to question 26. But before we do, I'm just getting set up over there. Let's actually see what they said here. So HCl is a strong acid, and HCN is also an acid, so that one won't even work. So B wouldn't work. D are two bases, and exactly. So with that, they're able to actually cancel out B and C, because as you see here, anything that involves HCl is an automatic L. So these two there, strong acids can't form buffers. So with that, this is correct. And now let's move on to the next question. Question 26. What are polar and non-polar covalent bonds? I'm glad that I broke down that, because I'm actually going to, well, not really cheat per se, but I'm actually going to copy and paste what we actually discussed earlier. We're going to go all the way over there. Why? Because I feel like this is actually, I would consider this gold. So I know we discussed electronegativity, so I'm going to do here is literally just copy this section. This is also for my notes as well. In fact, I guess I'll keep this stuff about Ionic. So let me copy that. Let's scroll now back down to question 26. Okay. And let's actually still write down the question. What are polar and non-polar covalent bonds? Okay, so with that being said, let's paste down what we had. Okay, so electronegativity difference, as discussed earlier, okay, I'm glad I actually was paste this down, is that it increases from the bottom left to the top right, fluorine being the most electronegative and francine being the least electronegative. Non-polar covalent bonds fall in this range of electronegativity difference. The most typical one you'll see, actually, at least if I remember correctly, is carbon and hydrogen. Those are, like, I guess, the most type of non-polar bond you would see. So carbon is 2.55, and hydrogen is 2.20. So let's actually change this then, because I believe it's actually 0.4, not 0.3. So that's embarrassing. Yes, so 0.4. Reason why I made this quick change is because you notice that carbon is 2.55 and hydrogen is 2.20 and 0.35. But I know for a fact, based on my previous knowledge, that hydrogen is known, hydrocarbon actually, that bond is known to be non-polar. So I'm just going to fix it here as well, just to keep things consistent for future notes. And yeah, so yeah, now we know. And there's also lists you can also find, not only your textbook, but actually in your textbook it should actually break down the electronegativity difference, because these are established in literature that this is what they usually refer to as being the cutoff for on different types of bonds. So now the question is asking, okay, what are polar and nonpolar covalent bonds? So nonpolar covalent bonds means that overall, right, when you have like carbon, hydrogen, okay, you wouldn't have a net charge, okay? These would be kind of equal. It wouldn't be leaning towards either side because the difference is 0.35, okay? Now if you had carbon chloride, okay, chlorine, okay, is 3.16 and carbon is 2.55. So 0.61, not the greatest difference, but it's big enough to where actually we actually use a sign here, okay? This means that it's gonna be more negative and that's gonna be more positive. We don't do it like ionic compounds where we just say like NaCl, whereas Na is positive, Cl is minus. We actually break it down like that because we're saying that it has a polarity, a negative polarity on the Cl and a positive polarity in this carbon, okay? So negative in the chlorine, positive in the carbon. That's usually how we indicate a polar bond, okay? And this right here, we actually would even have this because exactly there's no real polarity between C and H, okay? And as I mentioned here, the difference in electronegativity develops partial ionic charges due to the exactly unequal share of electrons. Point being is that the greater the electronegativity difference, the more polar it is, not the more ionic it is. Because ionic, as we discussed, it has to have a certain amount of electronegativity, plus the fact that it's a non-metal and a metal together. It needs those two criteria. But you notice that most things that do have a electronegativity difference greater than 2.0, it's mostly a metal and a non-metal paired together, okay? So methane is a good example of a non-polar covalent bond because of the fact that the CH's, that bond is not polar, okay? Water is an example of a polar covalent bond because not of the lone pairs, but specifically the bond between oxygen and hydrogen, that one, 2.20, and oxygen, based on the periodic table, is 3.44. Okay, so that's 1.24 difference. So just like how we drew the other one, it's going to be more negative on the oxygen, because it's always going to be more negative to the one that's greater in electronegativity, because as the name implies, electronegativity. So exactly, it's going to be more negative towards the oxygen. But yeah, so this is really the breakdown of it, and that's the oxygen hydrogen bonds in water. Now if you want to discuss whether the whole molecules are polar or non-polar, as I mentioned earlier, polar molecules just depend on how it's all balanced out. For example, and I'll say this example again, carbon tetrafluoride is a non-polar molecule with polar bonds. Okay, because Cl, they're all polar bonds, they have that difference. It's all electronegative in each corner. But because they're all evenly spread out, there's overall no net pull. That's a little bit of physics, you know. There's no net pull towards any direction because all the forces cancel out for a net of 0. So this is an example of a non-polar molecule with polar bonds. Okay, so correct. Okay, so now question 27. Like last session, we are going to 30 questions, just for you to, I guess, if you hear all the along the ride, you can prep to when, you know, I'll say that fateful goodbye. But now, let's talk about this. Methanol is a polar solvent, okay, is polar, and heptane is non-polar. Okay? And which of these two solvents are each of the following solids most likely to be soluble? So what does it mean to be soluble, right? I mean to be polar, right? We actually just discussed this. So methanol, right, has a specific, so meth is CH3OH, so it's going to be like, look like that, okay? So that's methanol, okay? And the way this works is, as we discussed, OH, it's has a polar bond, oxygen and hydrogen, and even oxygen and carbon has a polar bond, which is why exactly this oxygen here is where the negativity is, so that's where it's directed towards. But heptane is just, oops, that's pentane. This is heptane, filled with carbons and hydrogens. Net nothing, because of the fact that the difference between each carbon and each hydrogen is negligible, is less than 0.4, okay, for your electronegativity. So that's what they mean by this is non-polar. So it wants, so remember how the whole likes dissolve likes, okay? So we're actually gonna get first these options, and then we're gonna actually draw them out what they look and see if they have a polar or a non-polar side, to be able to see if it actually dissolves in, and it actually gives us the answer right there, really. But KCl, it says ionic, rubbing alcohol, okay, polar, gasoline, non-polar, and NaNO3, ionic. So let's start with KCl, ionic, okay? As we mentioned, when a metal and a non-metal bond, okay, the metal is just gonna be like, yeah, take my stuff, okay? And Cl is like, yeah, sure, if you insist. Okay, so now we have a negative and a positive side. And for the OH, we have actually a part of it, methanol. Yeah, methanol. We have actually a part of it that's a little bit more negative, and we have parts of it that are a little bit more positive. So actually, let me just note that. We have parts that are a little bit more positive, meaning that it actually has a polarity. And you know how it goes, opposites attract. So this oxygen will be attracted to that potassium, and the hydrogens and carbons will be attracted to chlorine, meaning that methanol is good to dissolve in here. Okay, why not heptane? Because the fact that heptane has no preference. It literally can't even, realistically speaking, connect with any of the KCl. It's hydrophobic. It has no, it's water hating in a sense. It doesn't have any means to actually dissolve in water, and also it means that for any ionic compounds, it won't interact with it. Now, rubbing alcohol, okay? So just to clarify exactly, only methanol can dissolve in the first one, KCl. For rubbing alcohol, the answer is actually in the name, alcohol. Methanol is a type of alcohol. So now we know, based on that, right, that whatever this alcohol is, it'll have some OH, okay? It'll be like some ROH. So because of that, we know that this is going to be the negative. This is most likely going to be the positive side, and it's going to work like that. Positive side again. Same interactions. Methanol likes that. Methanol actually has a way to attract it to that alcohol. So methanol will want to dissolve here, and heptane says, no thanks, I'm good. Again. Now, gasoline is a complete hydrocarbon. Okay? So, because of that, right, based on that name, it's only composed of hydrogen and carbons. And you notice that heptane is the same thing. So imagine we had a giant vat of heptane only, pretty much. That's the only place heptane would love to dissolve in. But now you come in with something that actually has a polarity, right? There's no way for it to really fit because it's in a non-polar environment. It wouldn't interact properly. It would not dissolve in it. So for this hydrocarbon, actually, only thing that would dissolve in it is heptane. So that's actually that answer there. So now for NaNO3, this one is going to be a shorter explanation because actually it works exactly like KCl. It even says ionic, so it's going to have that Na side, okay, and the NO3 minus, and then that polar side is going to go over to the positive. I mean, the polar negative oxygen is going to go over to the sodium, and the positive is going to go over to the nitrate. So with that being said, only methanol, because heptane once again says I'm good. So it's going to be methanol, methanol, heptane, methanol for each of these. Okay, let's see what they got. Exactly, they mentioned like dissolves like, which is what we discovered, and which is what we discussed when we said that we want polar to be with polar. Okay, and polarity, difference in electronegativities, we definitely mentioned that as well. We in fact used a previous question to help us answer that, and we know that heptane is a non-polar molecule because it's only filled with non-polar bonds. Okay, and methanol is a polar molecule. Okay, they mentioned the trend of electronegativity, which is what we saw here. Okay, and let's see what else they mentioned. Ionic compounds are polar because exactly they have the positive that's given away the electron completely, and the negative which accepted it completely. So with that being said, as I said, soluble in methanol, gasoline, soluble in heptane, and NaNO3, soluble in methanol. Okay, and the cool thing is actually is that everything this list is soluble in methanol would also be soluble in water, because the fact that water is also polar. So this is a nice tidbit, and exactly you've seen when you try to actually mix oil and water, just doesn't happen. That's what's happening with gasoline and such, because exactly oils and those things are typically mostly filled with just hydrocarbons, so they have not really any of a polar side, which is why they don't mix together. Non-polar and polar solvents don't mix. So yeah. So now let's move on to question 28. Depict the electron configuration for phosphorus using an orbital box diagram and a noble gas notation. So electron configuration for phosphorus using an orbital box diagram and noble gas notation. So let's actually go over to the periodic table. So noble gas notation means that we start at the noble gas. Okay, so we want phosphorus, so let's actually start here. Neon is a noble gas right before phosphorus. Okay, so that's how that works over there. And now we actually want to figure out the electron configuration. So it's going to be now 3, because now in the third row, so that's 3s2, okay, 3p3, okay, because there's only 1, 2, 3 right there. So that would be electron configuration, right? But it actually asks as well for the orbital box diagram as well. So although this is good, the orbital box diagram will look something like this. Okay. Okay, so it'll be 3s, 3p, 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 and the electrons will be, as I mentioned, there's 2. So this is filled up, but instead of it being 2 here and 1 there, it's actually going to be 1. It likes to fill at least 1 in each subshell first, then it will fill in the rest. So this will be electron configuration for phosphorus. Okay, and now they're going to ask one possible set of 4 quantum numbers for each of the electrons beyond those of the preceding normal gas. So it's talking about this row here in terms of the quantum numbers. They want the quantum numbers specifically from this section here, okay? So now let's actually break down what that means. So when you're dealing with electrons in the third shell, and how do you know it's a third shell? 3, okay? That's how you know. That means n is equal to 3, okay? Meaning that L, okay, which is the how I put this, like the type of orbitals you can have, is equal to the choices you can have are 0, 1, and 2, okay? And 0, so when L equals 0, that is the orbital, s orbital. Oops, I don't like that handwriting. When L, okay, I'm actually gonna make this a cursive L so it doesn't look like a 1. Okay, when L is equal to 1, that's a p orbital. And when L is equal to 2, that's a d orbital. Okay, and the d orbital, here's the thing about it. If you look at this periodic table, right, the d orbital actually starts on the 4th row. But the way the d orbitals work is that once you get into the 4th row, that d orbital is going to be n minus 1, if that makes sense, okay? Whatever row you have, minus 1. So for this case right here, as you notice for phosphorus, it doesn't have any d orbitals. This is just a possible orbital it could have if you're on the 3rd shell, okay? Now, this is actually where we get to the quantum numbers part. It's actually ML, okay? So ML is going to be every possible combination of 0, 1, and 2, okay? But positive and negative versions of it. So ML can actually be minus 2, okay? Minus 1, 0, 1, 2, okay? And now the last part, the MS, is just everything in between. Okay, so that's going to be minus 3 over 2, minus 1 over 2, 1 over 2, and 3 over 2, because it'll go like that. It'll go 2, 2 minus 3, 2 minus 1, 2 minus 1 half, to 0, to 1 half, to 1, to 3 half, to 2. And I told you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? But, funny enough, okay, let me just make sure I did this right. Yep, 0, 1, 2, 1 half. Now, as I mentioned though, okay, the 2's actually only apply to the D rows, okay? Because unfortunately, so I just need a little bit of water, but unfortunately, exactly, like, this only goes to P. So you can actually only focus on this part here. These are going to be the actual, as the question mentioned, the one possible set of 4 quantum numbers. Okay, so for this, in terms of phosphorus, okay, we don't need this as well because we don't have any d orbitals, right? So a possible quantum number would be 3, 0, 0. I'm just trying to actually think about this, sorry. 3, 0, 0, minus 1 half, okay? Any of those numbers would work. Another possible quantum number would be 3, 1, minus 1, minus 1 half. Actually, I'm probably doing this wrong. Let me just make sure. 3, 1, minus 1 half. Exactly. Exactly. Because the spin of the electrons inside. Exactly. Okay, good. So the spin, this one could be a positive as well, because exactly, when you actually look up at this, you notice that Just trying to make sure that I'm doing everything right. Yeah, this would actually be it. So 3s2 3p3, and as you hopefully drew it here, no they did not, would have been nice to actually show the electron shells, but you can pick any of these numbers as long as you understand that you don't have any 2s. So I in fact cross one different color. As long as you understand that these ones, because there's no D shell, it's gonna be that string of numbers. So any of these what's it called, quantum numbers would work for this question. Okay, so with that, that is the electron configuration for phosphorus. Okay, so let's move on to question 29 for today. Hopefully something that's a little bit simpler. Okay, alright, let's see here. Question 29. Is KOH an acid or a base? Amazing. Great. This is a question we can easily solve, because we want to know how it dissociates first. Okay, so KOH, acid or base? Okay, so with that, let's actually write our formula. KOH, aqueous, breaks down into K plus OH minus. So with that, we have OH, oof, wrong one. I don't know why I didn't switch. So we have OH minus. Right away, what do you remember about OH minus? That thing loves water. As in, if I put it with H plus, it turns into water. And you notice here, right, that it's two things becoming one. So there's a conjugate base, okay, and this is a conjugate acid, because the OH, okay, is now taking the hydrogen, well, I mean the proton, and turning into water. Okay, so with that being said, that makes KOH, because it has OH, a minus. KOH is not just a base, but it's a strong base, because OH minus is actually the strongest type of base you can have. So yeah, and let's see here into our acid base list. See OH minus all the way down here. Yes, it is quite a strong base to have. So KOH, K plus OH minus, OH and K, because K is also let's dissociate completely. They dissociate completely with each other, making this not just exactly a base, but a strong base. Okay. So with that, let's see what question we end with tonight. Hopefully something that we can actually solve. How can I write dissociation equations? So with this, actually, we can actually just use A, B's, and C, D's. So how can I write dissociation equations? So let's actually just use A plus B is equal to C plus D. Keep it simple for the last question of the night. So A plus B, C plus D. The way you write this, that's not a good example. Let's actually say A, B, A plus B. That's better, because you want it to be two things that dissociate into, one thing dissociates into two. The way you properly write this, okay, make sure you don't forget aqueous, but the arrow you put is not just one way, but you make sure you put its multi-directionality, unless you know for a fact that it dissociates 100%, like for example sodium. This is a correct way to show a dissociation equation. This here, okay, this right here is only for things that 100% dissociate. Examples are things like strong acids, most things bonded with sodium actually, so like NaCl. These things, in fact, I'm gonna make this all red if this can actually grab it. So yeah, I'm gonna make it all red. 100% dissociates. Strong acids, NaCl, this is that's it. But this is not. So not 100% dissociate. The most important thing here is really just the arrow, the signage, because you want to make that distinction. If they don't tell you that 100% dissociates, it's usually safer to just put that type of double arrow, okay? So this one is actually, they use salt, okay? This one is 100% dissociation, okay? So the chemical equation, actually, as we show, the second one, where it says one arrow pointing, turning into A plus B. So this is correct. But exactly, when you have things that are weak acids, so not 100% dissociate, so weak acids, you want to use this arrow here. The arrow is a key difference between 100% dissociating and not 100% dissociating, okay? So this is correct. Let's put that. And with that, we went through all those questions for tonight. Just want to thank you again for joining me this stream. Hope you have a wonderful rest of your night and enjoy the weekend coming up. Thanks again, and make sure you check the links in the description below if you need any extra help or if you want to review any of the material we covered today, okay? And with that, have a lovely night and see you next time.